and welcome to this video on OCR A acids. So this video is a revision video. My name is Chris Harris and I'm from AlleryTutors.com. And basically, I'm going to be going through this this PowerPoint, effectively, these slides. And it's basically just to go over the acids topic according to the specification. Now, these slides you can purchase. So if you just click on the link near the in the descriptions box, you'll be able to see it there. If you click on that, you'll be able to access them there. They'll be really good for things like revision. You can put them on your phone, complement the revision stuff that you've got already, and do what you need to do with it. Really, it's just another source of revision. Okay, so like I say, these are dedicated to OCR A, and it matches the specifications set out by them as well. So anything on here should be suitable for you if you're doing OCR A chemistry. Okay, right, so we're going to start with, obviously, this whole thing's about acids and bases. So the best place to start is to look at acids, bases, and alkalis as well. So we're just going to look at what they are and how they kind of interact with each other, etc. So acids are proton donors and bases are proton acceptors. Okay, you've got to remember that a little bit because that's really important. Okay, so when acids and bases react with water, they form a reversible reaction. And you can see here we've got obviously acids. Acids can be represented with HA, just means an acid, plus water, and it forms this H3O plus ion and A minus. And obviously this is actually what makes things acidic. We call it a hydroxonium ion or hydronium ion, it's also called. Bases are a little bit different. Again, I've used the word B to represent a base. Reacting with water, it forms BH plus and OH minus, and it's the OH minus that makes things basic. Okay, so we're looking for ions like this. So basically you're looking for either H3O plus or OH minus. An alkali is just, you might have, some people get these confused between an alkali and a base, but an alkali is just a soluble base. So a base that could dissolve in water. They produce OH minus ions, and when they're added to water, and this is obviously what makes it basic. Acids produce obviously this H3O plus that we mentioned before, but you don't really see it that much because we can simplify it really to just H plus. The H2O bit we can just eliminate because they only exist in water anyway, so we can just write H plus, and that's what we're going to be using from now on to represent an acid. But just have it at the back of your mind that actually this is what makes this ion, the presence of this ion makes it acidic. Okay, so let's look at the different types of acids bases. So a weak acid, for example, a weak acid would be something like ethanoic acid, other carboxylic acids, for example, they're looking for the COOH group at the end. Extra information, basically these reactions are reversible, and we say they dissociate, which means they break up. And actually in this reaction, when we talk about an equilibrium reaction, it means reaction go forwards and backwards. But in this reaction, equilibrium lies a little bit over to the left, over to this side. So the backwards reaction is favoured. So basically we have a lot of this and not much of these. Remember, it's this that makes it acidic. Strong acids are, sometimes these are also known as mineral acids. So these like hydrochloric acid, sulfuric acid, and nitric acid. These are examples of strong acids. Now, this one actually wouldn't really be reversible, to be honest, because these things are so strong. We assume they just dissociate fully. So HCl, for example, lies well over to the right if you had to symbolize it as an equilibrium. In reality, it wouldn't even be reversible. But you would have your H plus and Cl minus. This is basically just showing it for comparative purposes. Loads of H plus ions produced, very, very little to none HCl left because it breaks down very easily. Okay, strong bases. So sodium hydroxide, potassium hydroxide. These are examples of strong bases. A bit like a strong acid again. It's the reversible reaction is just there to comparative purposes. Loads of Na and OH minus. Remember, it's the OH minus that makes them basic. So we've got loads of these that makes them quite alkaline or quite basic. Very strongly ionizing, so they break up, dissociate strongly. Loads of OH minus is produced. And the opposite is your weak base. An example of a weak base is ammonia. Obviously, this is the opposite. These are reversible reactions. They are quite weak. But notice ammonia actually relies on water. We'll go through that later. But we need water there, and that produces the OH minus. But equilibrium actually lies well over to this side, so we don't get much OH minus, hence why they're weak base. Okay, so yeah, look at your OH. There's your H pluses. Just to make sure, obviously, you know that acids produce H pluses and bases produce OH minuses in solution. Okay, let's look at some of the acids for a moment. So we need to look at things like polyprotic acids. Okay, so some acids, they can donate more than one proton. We call them polyprotic, poly meaning more than one. Okay, so this one is a monoprotic one, just to kind of give you an idea. Nitric acid, what that means is if we have 1 mole of nitric acid, we will produce 1 mole of H plus ion, so it's a monoprotic. The first polyprotic, this is a polyprotic, is sulfuric acid, is what we call diprotic, because it produces 2 protons. So 1 mole of sulfuric acid will produce 2 moles of H plus ions, okay, which are protons. And another one is triprotic phosphoric acid, H3PO4. 1 mole of phosphoric acid produces 3 moles of H plus ions. As long as you can describe these as polyprotic, these two here, that's obviously monoprotic, but these two are polyprotic, di and triprotic. As long as you can describe them in terms of moles, that's the main thing. Okay, so acids and bases. Right, so acids react with bases to form salts, which are pH neutral. Okay, so salts are the neutral products of an acid-base reaction. So how this works in a very simple way is basically the H plus ions that come from the acid and the OH minus ions come from the alkalis. These make water, and water is obviously neutral. So this is basically just the ions. Now, the other ions involved in the acid and the alkali would produce the salt. So let's have a look at this example here. We've got an acid, hydrochloric acid, and the base, lithium hydroxide. We form lithium chloride and water. So salts are made from the metal of the base, or ammonium ion, depending on what we've got, and the non-metal, which is the other than the hydrogen, from the acid. So let's have a look in this example. There it is. So we've got the non-metal in the acid and the metal in the base. Now these two would react to form the salt. So this, in this case, is going to be lithium chloride. Let's have a look at this example. Nitric acid, HNO3, and potassium hydroxide produces potassium nitrate and water. Again, there's the non-metal in the acid, this bit here, and the metal in the base, and this forms potassium nitrate, so another salt. These are both salts, and then obviously we produce water as well. You've got to be careful with ammonia, like I say. Ammonia doesn't produce the OH minus ions directly. Look, it doesn't have any OHs, so unlike these two which do. So what it does is it actually relies on water for producing the OH minuses. So it does this by accepting a proton from the water, and it produces ammonium ions, which is NH4 plus, and OH minus ions. So that's quite important because you need to be able to write a reaction to show how ammonia can interact with water to form the OH minus ions. It doesn't have OH minus ions on its own. So ammonia actually reacts with acids to make ammonium salts, but no water is produced. Really important, a bit of a different reaction this. There's your ammonia, look. That's your base reacting with all your alkali, reacting with your sulfuric acid, and it produces ammonium sulfate. Okay, make sure it balances correctly. Obviously NH4 is plus, sulfate is 2 minus, so you need 2 of these to balance with your sulfate. And we form ammonium sulfate, so no water produced. Okay, so that's quite important. Okay, let's look at some different reactions. Now we need to know all these different reactions to do with acids and reacting with different things. So we'll start with the metals one first. So metals reacting with acids. So yes, so we can react them with metal and it'll produce salt and hydrogen. So that's the general reaction. We need to know an example. Here it is here. Calcium is a metal plus sulfuric acid produces calcium sulfate and hydrogen. Again, that's your salt, there's your hydrogen. The ionic equation is going to be this. Calcium, again, the sulfate bit is irrelevant, so we're just looking at the H plus bit because that's the acid bit. Produces calcium ions, again, ignore the sulfate bit, that hasn't changed. There's no change here, that's a spectator ion, and hydrogen gas. We need to know the equations, the ionic equations. You remove spectator ions from aqueous compounds. So obviously that's aqueous. The sulfate is the same left and right, so we can get rid of them. So we're only looking for changes in the reaction. Okay, let's look at the oxides. Right, metal oxides react with acids and they form salt and water. So it's just acid and base. So let's have a look at an example. Magnesium oxide reacting with hydrochloric acid forms your salt, magnesium chloride, and water. Make sure it's balanced. Make sure you know how to balance your the atoms as well within the molecule. So 1 Mg for 1 oxygen, because Mg is in group 2. The ionic equation, again, we're just looking for the bits that we're looking for, which are useful. So magnesium oxide stays the same. Look out for your aqueous compounds. We don't need the chloride. Chloride is the same left and right. Cl minus there, Cl minus there. H plus is the bit we're looking for. That's the acid bit. Reacts with Mg2 plus. Reacts to form, Mg2 plus, which is part of your salt, and water as well. So you can see here, this is the ionic equation for that reaction there. So remove the spectator ions. Okay, so metal hydroxides. So these react with acids to form salt and water. Very, very similar to oxides. Okay, except we're dealing with hydroxides, but it's the same thing. There's your hydroxide plus sulfuric acid in this case, forms sodium sulfate, Na2SO4, and water. And the ionic equation is OH minus. Again, the sodium, we can ignore the sodium. It's the same left and right. OH minus plus the H plus. Again, the sulfate we can ignore as well because that hasn't changed. So we ignore the sulfate plus H plus forms water. So this is the neutralization reaction. So you can see, if I show you the example, Na here and Na here is Na plus because they're both combined, so they haven't changed. And your sulfate is SO42 minus there and the same there, so that hasn't changed. So the only bits we're looking at is the H plus going to H2O. So we're just looking for changes. Okay, let's look at the metal carbonates. These are a little bit trickier. You've got an extra thing produced. Metal carbonate and acid produce salt plus carbon dioxide plus water. So you still produce your salt and water like all the other ones, like these, your oxides and hydroxides, except now we produce carbon dioxide because it's a carbonate. So lithium carbonate, here it is here, will react with nitric acid, HNO3, produce lithium nitrate, there's your salt, carbon dioxide and water. Again, look at your aqueous when looking for bits which haven't changed. The nitrate is the same, so we eliminate the nitrate when we write our ionic equation. And that's what we're going to put here. There it is. Lithium carbonate's a solid. We don't split that. H plus ions obviously come from there. Lithium, which is from there. Carbon dioxide and water. So that is the ionic equation for this reaction. So all of these you need to know. Obviously these are just example equations, but you need to be able to write an equation for any of these reactions. But you do need to know these general ones here. That is important. Okay, so let's look at the mole, okay, because obviously we're going to use acids and alkalis and things like titrations, and when we do titrations we need to know how to do molar calculations to do with solutions. So basically the number of moles in a substance in a solution can be calculated from concentration and volume. And here's the equation here, just as a reminder. You might have seen this in the amount of substance topic or in the amount of substance video. It's basically just a reminder. Your volume must be in centimeters cubed, in decimeters cubed, but if they give you it in centimeters cubed, you need to divide by 1,000. You can just add times 10 to the minus 3 to the end of that, to the end of the volume in centimeters cubed, and that will convert it into decimeters cubed already. And you'll see my example here, what I've done here. So calculate the number of moles in 200 centimeters cubed of 0.35 moles per dm cubed of HCl. So the number of moles is the concentration, which is that number, times by the volume, which is 200. Get that into decimeters cubed. So the reason how we do that is we take the number, the concentration, 0.35, times it by the volume, times by 10 to the minus 3. So that basically converts that into decimeters cubed, because that's the same as divide by 1,000. And we get the number of moles to be 0.07 mole. Okay, so there's the emphasis there. Okay, so times by 10 to the minus 3, it's the same thing. Make sure, again, if you've got any of these components here, any two of them, you can use this equation. Be prepared to rearrange it. Obviously, it's going to be vitally important when we do our titrations. Okay, which is what we're going to look at now. So your titrations. These can be used to work out the concentration of an acid or an alkali. Okay, so this is quite important. So what we do is we put an acid or an alkali in a burette, and we have a known concentration. We stick it in the burette here, which is this bit here, obviously on a clamp stand. We have an acid or an alkali. Again, it depends which, doesn't really matter which order you put it in. But we have an unknown concentration in here, but we have a known volume because we know how much we're going to put in here in the conical flask. And we're going to add a few drops of indicator into here as well. And we'll look at the indicators in a minute. The chemical, we add that using the into the conical flask. We basically keep adding it until the indicator changes colour. When it does that, we call this the end point. This is the point at which your acid and alkali have been neutralised. And basically near the end point, we add it drop by drop. Literally one drop of this can completely neutralise neutralise your solution. So you need to do it really slowly so you don't overshoot the end point and measure how much of this acid or alkali you've added to neutralise your acid or alkali in your conical flask. And when you're reading this, obviously, when you're measuring it, you're going to read how much chemical was added to the burette. Now, you have to read at the bottom of the meniscus. You can see this bubble here, okay? Always read it at eye level. You never read like above or below. You always read right on eye level and read at the bottom of this bubble here, okay? So this one reads 20 centimeters cube, not 19.8, as you may think on the top of the meniscus. Always at the bottom. Really important. Okay, and then you record your results to 2 decimal places. So when you take your reading from here, 2 decimal places, and you repeat your titration until you get 2 results which are concordant. So basically that means they're within 0.1 centimeter cubed of each other. And you take an average, and then you get your average titer from that. Your indicators, like we say, you can use are phenolphthalein. It's colourless in acid and pink in alkali, and methyl orange is another one. Again, it's yellow in an acid and red in an alkali. You just need to be able to be aware of these colours and know, obviously, what colour they are depending on what solution is in there. So, for example, if I had an acid in here, add my indicator, it would be colourless. And as I add my chemical, as soon as I get this permanent pink colour appear in the flask, it's neutralised, and I stop adding the reagent from the burette, and then I measure it using this technique over here. Okay, now we need to be able to make a standard solution. So this is a solution that we are going to test either in here, or we can use it in this burette here. Okay, so these are used in titrations. We have a known concentration because we're making it, so we can work out the concentration. So in this example, we'll assume that we know the concentration of the chemical in the burette. Okay, this is because it's made as a standard solution. Okay, but it could be the other way around. So we know the concentration of this. So we can titrate this standard solution against the unknown concentration in the conical flask here. And basically the standard solutions are made from solids with a known mass. And they're dissolved in water to a fixed volume in a volumetric flask, as you can see on here. And we can work out the concentration of this stuff too. Obviously, we'll look at this, we'll look at the method, because you need to know the method of how to make a standard solution. We'll look at this on the next slide. Okay, so methods. So the first thing we have to do when we're making a standard solution, if it's a solid, normally it is. So for example, it could be sodium hydroxide. We're making sodium hydroxide solution. So we take the sodium hydroxide, which is a solid, and we weigh it first. Okay, we're going to weigh it precisely. We use a balance and a glass or plastic weighing boat. So we just put it into there and measure it out precisely. Then we have to transfer it. We're going to transfer the solid we've just weighed out from the weighing boat into a beaker. We're going to wash any solid left behind into the beaker using deionized water. The reason why we wash them out is to make sure that we've got all of the stuff that we've weighed is being transferred into the beaker. Deionized water just prevents any, if there's any ions in there, they could react with your solid that you've just weighed out. So we use deionized water for that reason. Then we have to do is dissolve it. So we're going to dissolve our solid fully using deionized water, and we stir to ensure the solid is dissolved fully. So we've got the solid in here, adding more deionized water, and we keep on stirring. We want it to be fully dissolved, or as dissolved as we possibly can. Then once we've done that, remember we're still in the beaker, we need to transfer this into our volumetric flask. That was the big flask that I showed you before. Use a funnel, okay, because otherwise you'll get it all over the place, and you don't want to lose any of the product you've just weighed out. So really carefully using a funnel, rinse the beaker and the glass rod that you've stirred it with. Really important. You do have some residue left on that glass rod. You want everything in that volumetric flask. You don't want to waste anything. Also, might be a good idea to rinse the funnel as well, because you might have some residue left on there. Basically, rinse everything that's been in contact with your substance to make sure everything goes into your volumetric flask. And then once we've done it, we need to fill the volumetric flask. So using more deionized water to the graduation line. There's a little fine line at the neck of the volumetric flask, and we need to again fill there, measure to the bottom of the meniscus. Okay, so we don't want to go above the line, otherwise we're not using an accurate volume. Okay, use the pipette when we get near the line, so drop by drop until you get literally just to the bottom of the meniscus. Really important to measure it carefully. And then once we've done that, we've got to mix it. So we invert the flask, give it a good shake, put the lid on it. Of course, you don't want the solution going everywhere, and make sure it's thoroughly mixed, and then your standard solution is ready to go. So it's as simple as that, pretty much. All these little bits here, make sure you know these little intricate details and why you need to know them. Really important. Okay, so let's look at some calculations. So let's say we're going to might ask a question like this. What mass of solid sodium hydroxide is required to make 250 centimeters cubed of 0.75 moles per dm cubed sodium hydroxide solution? So I want to make this volume of this concentration of sodium hydroxide. Sodium hydroxide is a solid. When you buy it, it doesn't come as a liquid. You buy it as a solid, and you have to make up the solution yourself to get the right concentration. It's handy because it means you make whatever concentration you want, just about. So first thing, work out the number of moles of the solution you want to make. Okay, so moles, we've obviously got a volume, we've got a concentration. Look, so from this we can work out the moles. So moles is concentration times volume. Volume's got to be in decimeters cubed. So moles is 0.75 times by 250 times 10 to the minus 3. Remember, this is dividing by 1,000, converts into decimeters cubed. That's why we've put that on there, remember from the previous slide. Number of moles, 0.1875 moles. That's the amount that we need to make. So we're going to use this number of moles, or these number of moles, from the previous step, this one here, and we're going to calculate the mass. Okay, so we know the number of moles, and we can work out the mass by doing moles times by relative formula mass. This is in grams per mole. Now this is of your sodium hydroxide. So using your periodic table, work out the relative formula mass, sodium plus oxygen plus hydrogen, and then we add them up and we get a total relative formula mass of 40. Multiply by the number of moles, and we get the mass, which is 7.5 grams. That should say mass on there, not moles. Okay, so obviously because this is a mass, so it's 7.5 grams. Okay, relative formula mass, like I say, of sodium hydroxide, 23 plus 16 plus 1 is 40. So just quickly going back to this, actually, this mass here, that is the amount of sodium hydroxide that we need to use to make 250 centimeters cubed of this strength sodium hydroxide. Obviously, if I wanted this to be stronger, I'm going to have to add more sodium hydroxide or a larger mass. Okay, right, titration calculations. So titrations can be used to work out the concentration of an acid or an alkali. So let's go through a worked example. 18.3 centimeters cubed of 0.25 moles per dm cubed HCl was required to neutralize 25 centimeters cubed of potassium hydroxide. Calculate the concentration of potassium hydroxide. Okay, so the first thing we have to do is write out an equation, make sure it's balanced. So here's the equation: acid, alkali, salt, water, all balanced, ready to go. Okay, adding a hydrochloric acid in here, so potassium hydroxide in your conical flask. Okay, then what we can do is calculate the number of moles of HCl, because we have a volume, we have a concentration of HCl, so we can work out the number of moles. And once we know the number of moles of HCl, we can actually use it to work out the moles of any one of these substances. So that's pretty useful. So moles equals concentration times volume. Concentration is 0.25 times by the volume, which is 18.3. Remember, we have to convert to centimeters cubed. To decimeters cubed. So we take the value in centimeters cubed, times it by 10 to the minus 3. That converts it into decimeters cubed. And then we get a number of moles as 4.58 times by 10 to the minus 3. And this is the number of moles of HCl. Okay, so yeah, make sure it's converted to decimeters cubed. Then we use the equation to find out the molar ratio in order to work out the number of moles of KOH. We call this stoichiometry. So basically, we've got a 1-to-1 ratio between HCl and potassium hydroxide. You can see we've got 1 and 1. Okay, so 1-to-1 ratio. So the number of moles of this is going to be the same as the number of moles of this. So we're going to get the number of moles of potassium hydroxide in that case to be 4.58 times by 10 to the minus 3. So now we know the moles of this and we know the volume, because they've told us the volume, we can now work out the concentration. So we do it like this. So concentration is the number of moles divided by the volume. Okay, so moles per decimeters cubed. And so we use this and we put the numbers in. Number of moles is 4.58 times by 10 to the minus 3 divided by 25 times by 10 to the minus 3. That's obviously in centimeters cubed. So we add the times 10 to the minus 3 to convert to decimeters cubed, and we get our value of 0.18 moles per decimeters cubed. So you've worked out the concentration of potassium hydroxide in here by doing a titration. It's pretty straightforward. Make sure you follow these steps methodically. Okay, let's look at another example. So we can also work out the volume of an acid or an alkali. So here's another example. 15.7 centimeters cubed of 0.45 moles per dm cubed H2SO4 was required to neutralize 0.120 moles per dm cubed of sodium hydroxide. Calculate the volume of sodium hydroxide being neutralized in centimeters cubed. Right, so let's have a look. Write our equation. Different equation this time. Sulfuric acid plus sodium hydroxide forms sodium sulfate and water. So acids plus base gives salt plus water. Okay, there's the acid in the burette. Sodium hydroxide is in your conical flask. Okay, so we're going to calculate the number of moles of sulfuric acid. So again, we've got a volume, we've got a concentration, so we can work out the moles. So concentration times volume. Again, volume converted into decimeters cubed. This bit here. There it is. Okay, so there's the times 10 to the minus 3. That's the volume. Concentration 0.45 times by 15.7 times 10 to the minus 3 gives you the number of moles of sulfuric acid. We use the molar ratio to work out the moles of sodium hydroxide. Now this time it's a 1-to-2 ratio. Okay, 1-to-2 ratio between sulfuric acid and sodium hydroxide. So the number of moles of sodium hydroxide is 2 times the number of moles of sulfuric acid. So this is going to be 2 times by 7.07 times by 10 to the minus 3, which is this, equals 0.0141 moles. This is the number of moles of sodium hydroxide. Now we want to work out a volume. We have a concentration of sodium hydroxide and we have a moles, so we can work out the volume. So the volume in decimeters cubed is moles divided by concentration. So the moles is 0.0141 divided by 0.120. That will give you a volume of 0.118 decimeters cubed. The question said we need it in centimeters cubed though. So how we're going to do that is going to take this, times it by 1,000, and that will get it back into centimeters cubed. So the volume in here would be 118 centimeters cubed of sodium hydroxide. So pretty much the same. You can see the method is very, very similar. And that's it. That's the bits for acids for the OCR A specification. You can see the little circle in the middle of the screen. You can click on that and you can subscribe to the channel, and you can see all the updates on the videos that we put on. Also, just a reminder, if you want to get a hold of this PowerPoint, you can purchase it. Just click on the link in the description box. But that's it. Bye bye.